Um, Before getting started, I'd like to preface today's webinar with a brief update on the global climate. Yesterday, the World Meteorological Organization, which is a specialized agency of the United Nations, reported that 2020 was one of the 3 warmest years on record, coming in at 1.2 degrees Celsius warmer than pre-industrial times. The Arctic, which is now warming at twice the global rate due to a phenomenon known as Arctic amplification, recorded its highest ever temperatures north of the Arctic Circle, registering 38 degrees Celsius or over 100 degrees Fahrenheit on June 20th, 2020. In response to the report yesterday, the Secretary General of the United Nations warned that humanity stands at the verge of an abyss. And many experts agree that we're now facing the possibility of an ice-free Arctic summer as early as 2030. That's within the next decade. And I'm sure that Dr. Peter Wadhams, when he provides his presentation, can speak firsthand about how he's seen the Arctic vanish before his eyes during his career, having executed over 50 polar expeditions over the past 30 years. Now, while I shared that news, that's a little bit gloomy, I'd also like to share some good news, which is that although the Arctic's future is uncertain, a lot of good work is being done. Science-based solutions are emerging, and there's a growing consensus that we have the know-how or the brains to slow down the pace of climate change. One of those additive solutions will be spoken to today by Dr. Field, which is Arctic Ice Project's sea ice surface albedo modification technique, which can be applied in targeted areas of the Arctic to actually increase the reflectivity of Arctic ice, reflect more solar radiation back into space, and serve as have a net cooling effect over this precious ecosystem, which is the Arctic. Another positive trend is that our society is finally beginning to break through the politics so that we can confront climate change. We all know that philanthropy is not scalable and it's not sustainable. In the long run, we're going to need the federal government or the world's governments to intervene along with civil society to fund these science-based solutions, as well as to decarbonize the world's the planet's economies. Last month, the National Academies of Sciences, Engineering, and Medicine issued first-time recommendations to establish a solar geoengineering research program across federal agencies and scientific disciplines of up to $200 million. Now, while $200 million is obviously a drop in the bucket in terms of our federal budget and an infinitesimally small number in terms of the climate devastation that will be in the trillions to the world's economies, it does represent a great leap forward in terms of the federal government's engagement with common sense solutions to climate change. And I'm sure that our speakers today will be able to speak to how positive that is, and because they've been working in the sector for decades. Until that federal funding arrives, as I'll remind the audience, organizations like the Arctic Ice Project rely upon private philanthropic donations to fund our scientific work and the scientists that do our work abroad. Now, the purpose of today's meeting is really to bring the voice of the scientists and the innovators into this room and not to hear from the MBAs like myself. So I'd like to pause there, get off my soapbox, and I finish my spiel, and take a moment to introduce our prestigious panelists. First, I would like to welcome Dr. Peter Wadhams. And I should have prefaced today's introduction with also a thank you to Peter, who's dialing in from the United Kingdom today. We know you have a busy schedule and we appreciate the time you've allotted us, but especially given the late hour, so that we can have live Q&A with our supporters in the Bay Area during Earth Week. It's really appreciated. Dr. Peter Wadhams is the Professor Emeritus of Ocean Physics at the University of Cambridge. He's a gem in the UK. He's the UK's most experienced sea ice scientist with more than 50 expeditions to both polar regions. During his career, he's worked on ice camps, icebreakers, aircraft, and my own favorite, Royal Navy submarines, having made 6 submerged voyages to the North Pole. Dr. Wadhams is well known for his vast work studying the Arctic ice, as well as his marvelous must-read book, A Farewell to Ice, which I recommend to our audience. It was included in our actually Invite Bright invitation. I really recommend that people read this book. And personally, I've always considered Dr. Wadhams kind of the Indiana Jones amongst the polar scientists. I'd also like to introduce our next speaker, Dr. Leslie Field. Dr. Field has been leading the fight to slow climate devastation since 2006. She has degrees from MIT and UC Berkeley and is an inventor with 58 issued US patents. She has worked at HP Labs and Agilent Labs and founded 2 technical MEMS consulting companies. She also serves as an adjunct lecturer at Stanford University, where she teaches a highly ranked annual fall quarter class on engineering, entrepreneurship, and climate change. So before I move on to the panelist presentations, beginning with Dr. Wadhams, I also think a picture shows 1,000 words, or in this case, a video. So I'd like to show the audience 2 back-to-back videos of our respective organizations. The first is an excerpt from featuring Dr. Peter Wadhams, which is from the 2009 documentary film Ice on Fire, which was produced and narrated by Leonardo DiCaprio. And the second, with Dr. Fields, is an excerpt from a Vice News brief on the Arctic Ice Project, formerly known as Ice 911. So with that said, I'll start the video now.
I've been working on sea ice for the last 50 years, pretty much, and the whole Arctic has changed so much in that time. Loss of ice, loss of not only the loss of area of ice, but the loss of the appearance of the great ice fields of the past, with huge pressure ridges, very, very thick ice, really dramatic ice scenery has all gone. Last month, I was up in the Barents Sea on a research cruise in a region where normally you would have quite a lot of multi-year ice. We couldn't find any multi-year ice. So the ice was all very thin, 30 centimeters thick. The Arctic Ocean is no longer a continent of ice, but something that becomes just water in summer. So it's a huge loss as far as beauty is concerned, but also as far as the physics of how the planet operates. The ice is disappearing because the climate's warming. That's pretty obvious that will happen, but there's much more to it than that, because in fact you have many other feedback mechanisms going on which cause the effects on the planet to be far worse than just the retreat of the ice. So the Arctic's warming up 3 times faster than the rest of the world, and the temperature difference between the Arctic and lower latitudes is getting less. And that means that the jet stream is getting to be weaker. And as it gets weaker, it goes from being almost a straight line to becoming big lobes reaching up north and south. And when you have a lobe like that, it means that polar air can come down to lower latitudes than it normally reaches in one sector, and then in the sector to the east or west of it, you've got warm air going up north further than it should do. So you're getting bizarre weather extremes, which of course everybody's been commenting on. And the trouble is, where these air masses are causing such extreme changes happens to be the latitudes at which you have the maximum food production. Suddenly our ability to feed everyone is being affected by these polar changes. You can't take that amount of ice away without affecting so many other things.
The impact of our actions are starting to hit home. Scientists' predictions are now coming true sooner than expected. We are tragically suffering through severe storms, droughts, floods, and fires that are progressively becoming more intense and more unpredictable.
in one experimental site in the Arctic, a scientific team is focusing their work on the ice itself. So we sent Ben Anderson to Alaska's northernmost town.
This is hollow glass microspheres. You can think of it as a form of floating sand. It's reflective, it's bright. It's basically a thin silica shell around a gas core.
I mean, a lot of these things seem to be about damage limitation, but this is actually about boosting the ability of the ice
we're working on Arctic restoration. People are attributing a quarter to a half of global temperature rise every year, right now, is coming from the loss of that reflective heat shield in the Arctic. We want to build that back to be the Earth's heat shield, the Earth's refrigerator.
The idea is surprisingly simple. Cover the ice with reflective sand to reduce the amount of sunlight absorbed. The team is testing the concept on a small scale on a nearby frozen lake.
Based on what you've done so far, this area will be covered with your reflective sand. Roughly how much longer will the ice last?
The prediction is days, and that matters on this scale.
The long-term goal is to scale up the process and pinpoint the areas in the Arctic where it will have the greatest effect.
We're looking at areas on the order of 0.5% of the Arctic. By building that back, you stop this inevitable heating feedback loop of getting things hotter and hotter and sea levels rising and destabilizing the jet stream and having more severe storms and such. Rebuilding ice would be easier on the wildlife, would be easier on the planet. Is one of the safest things we can think of to be able to turn back to where we were. And the idea is to try to rebuild a natural system with the least possible intervention you can possibly make. We really have to preserve the Arctic. There's no option there, and we have to proceed with all due speed on all these other mitigation techniques that people are using. I mean, this is just, it's key. It's absolutely essential. They have to work together.
So Peter, I think that provides an excellent high-level view of both the topics at hand. I'll hand it over to you to share your screen and begin your presentation.
Okay, thanks. So yeah. Right, hope this. Wow, this works. I'm always terrified things are not going to. So what I want to talk about is leading on towards what Leslie's going to say is just to try to explain why we feel an urgency about restoring Arctic ice, or at least not letting it disappear, why that's important above many other things in dealing with climate change. And it's basically because the loss of ice will have so many other feedback effects which are harmful on the planet. So it's very, very urgent that we actually deal with the problem of not letting the ice disappear, or trying to bring it back, independent of cooling the climate of the planet as a whole, although that's something we have to do. But how and why do we want to emphasize the Arctic above all else? Okay. Well, because everybody always advertises their own books, so this is the book that has been mentioned, A Farewell to Ice, available at all good bookshops. And then the film that they showed a small piece of is also something you can go and see, or you can go and view a pirated version at home called Ice on Fire, which was produced by Leonardo DiCaprio. And it is a very original film, very brave, in fact, because he doesn't just deal with the normal thing, which is we must reduce our carbon emissions or else. What he's dealing with is the fact that we have to take carbon dioxide out of the atmosphere as well, find ways to do that, because simply reducing our carbon emissions will just result in us warming more slowly. It won't be a way in which we can cool the climate. So he looks at all the ways that we can take carbon dioxide out of the atmosphere. So it's a very good film in that respect, and an unusually courageous one. So here's the problem, that here we see the last 400,000 years, and what has happened to global climate and carbon dioxide and sea level during that time. We've been through a series of ice ages, each of which lasts about 100,000 years. And the ice ages tend to adopt a kind of sawtooth history. The world declines very slowly into an ice age. The glaciers grow in thickness, ice sheets get thicker, the climate gets colder. Eventually we're in the depth of an ice age, and then we come out of it remarkably quickly. Suddenly, not suddenly, but within a few thousand years, we're out of that ice age, and then we start heading slowly towards the next one. But the last one we had, things happened differently. We went down slowly from the interglacial period towards the depth of the ice age. We came out quickly, but then unfortunately, man became too clever and started to develop an industrial society. We discovered that we could get a lot of energy out of burning fossil fuels, and we started a civilization based on fossil fuel burning. And at first we didn't know that that was doing any harm, but it was, of course. And the first thing it did was to drive up the carbon dioxide level in the atmosphere to way beyond what it was at the end of the ice age. The ends of ice ages, the warm periods, seem to be some kind of standard level of CO2, about 280 parts per million. So we came up to that level, but then when we started to burn coal and eventually oil, up shot the CO2 level, and it's now up to about 420. And that does something drastic to our planet. And this is something where the world has never had that level of carbon dioxide for about 50 million years. So we've done something inadvertently which has really screwed up the world's climate. And at the same time as the CO2 level following this sawtooth pattern, the global temperatures have followed the same sawtooth pattern, and sea level has more or less followed that pattern as well. The data on sea level is not so good, but you can see that it follows about the same pattern, mainly because when we're warming the climate through increasing the CO2 level, the warmer climate results in less sea ice. And when we have less sea ice, we tending to have warmer air over land ice masses like the Greenland ice sheet, the Antarctic ice sheet. And the result is that they melt faster and we get a more rapid rise in sea level. So sea level seems to be correlated with carbon dioxide level as well as with temperature level. And in the last 1,000 years, we've had some better data on this. Mainly from trying to correlate ice cores taken from Greenland and Antarctica with various other sources of information, like cores taken from tree rings. And the picture was over the last 1,000 years that the Earth was gradually cooling towards a new ice age, which is due in about 20,000 years' time. The trouble was, in the middle of the 19th century, that stopped happening, and suddenly the temperature started shooting up. Now, I don't know if you can you see the right-hand side of this thing? I've got some of the people's faces are in front of it, but sorry, I can't actually.
We can see it.
You can see it. Okay. Can I see? Can I get these out? Yeah. Okay. There we are. Good. Okay. Thanks. So this shooting up of the carbon dioxide level was accompanied by also a very rapid increase in methane and nitrous oxide. Now, all of these are greenhouse gases. That is to say, they absorb a lot of the outgoing radiation from the planet and hold it in so the planet warms up. And so we've been suffering from greenhouse-induced warming ever since we started putting artificially these extra amounts of these gases into the atmosphere. And we didn't know why. For about 100 years or so, we were living with the Industrial Revolution, but we had no idea what it was doing to us. But in 1896, various new physical laws having been discovered about how gases behave, there was a classic paper produced by Svante Arrhenius, who was a Swedish scientist, about what carbon dioxide would do when released into the air. And he found, the results he found were actually very accurate in relation to what we know now. And of course, it was called carbonic acid then. He found that the amounts being produced and the way in which that was causing warming of the planet were very much as we now know today. But he thought that most of the heat will be absorbed by the ocean, and so it wouldn't cause any particular upset to mankind. Of course, he was wrong. But in other respects, he was right. And he, by the way, he was an ancestor, I think a great uncle of Greta Thunberg. So she's got a pedigree in climate change research. And this was 1896, and we still didn't do anything. Then we knew what we were doing, that we were doing something to the atmosphere, we were warming the climate, but we still didn't take any action. In fact, we still haven't taken any action. And it wasn't until 1958 that somebody thought, hey, why aren't we monitoring the CO2 level in the atmosphere, see how high it's getting? So that started then from an observatory on the top of Mauna Loa in Hawaii, and it was done by the Scripps Institution of Oceanography. So they've been taking daily measurements from there, and various other observatories have been added ever since. And we see, sadly, this very revealing curve that the carbon dioxide level in the atmosphere has been rising. It's been rising at an accelerating rate, and nothing that we've done has had the slightest effect on it. All of the agreements that politicians have come to about the Copenhagen Agreement, various other agreements leading up to the Paris Agreement in 2015, which is over here, that didn't have the slightest effect. That we continue to put carbon dioxide into the atmosphere, we continue to increase the warming of the planet as a result, and we don't seem to be capable of slowing down the extent to which we put CO2 into the atmosphere. So it's an extremely dispiriting graph here that we see. We're really continuing to do great harm to our planet at an increasing rate. This is more than an exponential rate of growth. Where's it all coming from? Well, there are various villains that are worse than other villains. The USA used to be the worst villain, but now, partly as a result of the US and Europe transferring a lot of their industry to China, the biggest villain has become China, with India coming close behind in terms of carbon dioxide emissions, because they've now got most of the world's industry. And they also have a tendency to keep mining coal and building coal, making coal-fired power stations, which are very, very profligate in carbon dioxide emissions. And also, this graph mentions cement, that cement is especially evil as far as climate change is concerned, because you don't have, not only do you have to use a lot of energy to produce cement, and that produces carbon dioxide, but also the chemical reaction that produces cement produces carbon dioxide as well. So cement is the worst thing you can use to build anything out of. You shouldn't be building buildings out of concrete, but we do. So that's what we've been doing, and it's been obviously having an effect on warming the planet. And the first thing that happens when you warm a planet that's got some region of itself that's at less than 0 degrees is you melt ice. And we first started to see this from what happened to the Arctic Ocean. The Arctic Ocean used to have a cycle where in the winter, the whole Arctic Ocean and a lot of the seas around it were sea ice covered. In the summer, the central Arctic Ocean was still sea ice covered, so that the European and American continents still felt as if they were glued together, and the northern hemisphere of the Earth was like one landmass. However, as the warming proceeded, the summer extent started to become obviously reduced, and the black line here is what the typical summer extent used to be, and then via a number of steps downwards, we got to here, which is where we were in 2012, a very big decrease. About half of the ice in the Arctic disappears in half the area, and so we're now down from the yellow line to the white, and worse than that. That's the extent has been going down, and 2019 was a almost record year. 2020 was even more of a record year for the ice to come to a very low value in the summer, which is September in the Northern Hemisphere, and then be very slow in re-establishing itself in the following winter. So this is how the summer extent has decreased over the past 30 years. And when you go to the Arctic every year, you notice a difference. This is what I used to see when in the early 70s, when I used to go out on the Arctic Ocean, and most of the ice was multi-year ice then. That's ice that's many years old. Some of it melts in the summer, it grows some more in the winter. It gets to look like a really rugged landscape, a bit like the Grand Canyon. That's what you used to get. But what you get now is, well, I was going to say it's the background of this picture. That is the ice is first year ice. It's very thin, it hasn't got many ridges. You can, in places, you can fall through it. And here we have a place where people have been falling through. It's northwest Greenland, the sea ice off northwest Greenland, with a couple of Inuit polar bear hunters. And they've been finding that with these heavy sledges, they've been going through the ice, and some of them have been drowned. So there's been a project with the European Union where we've been fitting these sledges with radar on their wooden sledges, a radar warning device on the bottom of the sledge, which gives a warning if the ice is very thin. So plus, of course, giving you some data on ice thickness. So this has helped to save some lives up there. But we see the difference, for instance, with first-year ice. It can't resist wind stress. So we have these massive amounts of leads. And this is at the middle of the winter in March 2013. Instead of having solid ice over the whole Arctic Ocean, we have this array of leads. That's lanes of open water. And it means that, for instance, you can't establish anymore this sort of thing you used to have in the Arctic in the winter, which was nice ice camps, which you could live on for a few months and be supplied by air, because you can't safely land an aircraft anymore. So we've been measuring thickness as well as extent, and when you combine the two, you get an even more frightening result, because the average area of the Arctic ice has gone down by about 50% since the 1970s, but also the thickness has gone down by 50% as well. So if you combine the two, the volume has gone down by about 75%. So here we see a difference from the late 1970s until the early 2010s, and it's a loss of 75% of the summer ice has gone, and soon all of it will have gone. But it already has other impacts. For instance, with the ice gone in the summer, you have much warmer air over the Arctic Ocean. That air moves over the Greenland ice sheet, and so we have warmer air over what used to be always a frozen mass, because the Greenland ice sheet has a very high altitude. It's about 3,000, 4,000 meters above sea level. Normally, even in the summer, you wouldn't get any melting of that, but we do now. And here we find that in the summer of 2012, almost the whole Greenland ice sheet was covered with meltwater. And the mass of the Greenland ice sheet is reducing at an accelerating rate as the ice melts. This is measured with a gravity satellite. And here we are. Here I was fortunately enough to be visiting the Greenland ice sheet on the day in which there was the biggest single day's loss of ice from Greenland ever recorded up to now, which was 12.5 billion tons in one day. And the reason why there was such a lot of loss was that it was warmer. It was 21 degrees on top of the ice sheet, which is unprecedented temperature to have on a 3,000 meter high ice sheet. And we could see another effect going on, which was really dangerous, is the fact that as the ice sheet melts and the ice drains away in the form of meltwater rivulets, little waterfalls, the water's going, but it's leaving the dirt behind. So as the ice sheet's sinking down, with water disappearing, going out to the ocean, raising sea level, but the dirt is left behind, and this gives you what's called black ice. And but that dirt, because it's dark, is absorbing radiation at an increased rate because it's got a low albedo, and that loss of heat is sort of loss of is causing the ice sheet to lose mass even faster. So the black ice is causing an accelerated loss. So here's some, and now where you see huge areas of this dark ice cover over the top of what used to be white ice. Not only that, but the land ice is also disappearing. This is land ice, but the snow on land rather is disappearing as well. We used, for instance, to think of Alaska and Siberia as places that are permanently snow covered, the white hell of the Arctic. But these brown areas show areas that in summer now are ice free. So you have tundra, forest. You don't have snow over those areas anymore, and that also reduces the albedo because you're not covering this area with white stuff in the summer. You're covering it with dirty brown stuff, which includes tundra and forest. And the dirt, of course, comes from a lot of different sources. We're studying that at the moment. One of them is actually airborne soot from fires. This is a fire I happened to drive past. You can't avoid driving past fires in California, as Leslie will tell you. This is Pasadena, which I always thought of as a big city, but in fact it seems to have a lot of combustible material in it. That's one effect that the sea ice retreat is having. Another one is a real threat that we should be worrying about enormously, but we're not, or at least the Intergovernmental Panel on Climate Change isn't worried about it, which is that the Arctic seabed in the shallow water parts of the Arctic, which is about a third of the Arctic Ocean, all this light area here, is shallow water, and under that shallow water there's a very thick layer of sediment that's rich in methane, and the methane is combined chemically with the sediment to give you chemicals called methane hydrates, and they're stable so long as you've got something on top of them to hold them down. And what does that is, at the moment, permafrost, a sort of some seabed layer of permafrost. But the permafrost is melting or thawing because the seawater that's lying on top of it is itself warming up. The sea ice retreats, leaves open water in summer. The open water warms up. The water is shallow, so the warm water reaches the bottom. The warm water at the seabed causes the permafrost to melt, allowing the methane to come out as a gas. And there's frightening data now of methane plumes rising from the seabed. This is shallow water because it's coastal seas, 70 meters deep, and methane plumes shown here from sonar measurements just coming up, vomiting out methane into the atmosphere. The methane can't dissolve because it's too short a rise time, and that gives you an increased methane level in the atmosphere, which is now causing methane levels to be rising steadily and in an accelerating way, and that's increasing our rate of planetary warming because methane is such a powerful greenhouse gas. This shows methane bubbles coming up to the surface from deep down. This is some Russian data, and we're seeing now wherever we measure methane, this is a methane site in the north of Canada, we see methane levels rising. Another effect, there's too many effects to have time to talk about them all, but another one that has been recognized recently, which you've experienced, is that the Arctic, because the Arctic is warming faster than the tropics, the air mass over the Arctic Ocean is getting warmer relative to the air mass over the tropics. That temperature difference is reduced, and that reduces the strength of the wind that separates these two air masses, called the jet stream. The jet stream takes on this lobed pattern, and with a lobed pattern, you find that allows cold air to come from the Arctic to come down to lower latitudes, and warm air from the tropics to rise to higher latitudes. So in between, where the jet stream is sitting, we have extreme weather events, either hot or cold, and that just happens to be where we grow most of our crops. So there's a threat to the productivity of the planet for growing food crops, and that's something which is having a bigger and bigger effect. We can detect it just from the price of food. The UN has a food price index for the average price of food worldwide. They started it at 100 in the year 2000, and it's already gone up to beyond 200, came down, went up again. And that's causing tremendous hardship in cities in the third world where people can't grow their own crops and are very poor. So it's causing a lot of violent unrest. Also, as the temperature rises generally, the yield of all of the food crops that we have is beginning to go down. And if as temperature rise gets greater, the yields of crops, regardless of these special events, goes down. So I'll what I'm trying to say is we've got to do something about this, and we must be really worried about the Arctic and about the loss of ice and what it's doing to having all these other impacts on climate. So it's really important to try to bring back the Arctic ice, and there are different ways of trying to do that. Leslie will be talking about the various methods we can use, but it's a very difficult one because the difficult task is to save the climate. We have to do something drastic to the entire planet, and the things, as Greta has reminded us, and one of those things is we've got to not only reduce our carbon emissions, but we've got to actually get rid of carbon dioxide out of the atmosphere as well, which means developing techniques for running running air through systems that remove CO2 and do something with it, put it somewhere, put it underground, or turn it into some solid rock. Or we have to do the same to something in the ocean as well, try and increase the amount of CO2 that we get rid of from the oceans, for instance, by growing a lot of kelp. These are worldwide things we have to do, but regardless of that, we have a special responsibility to get rid of ice. Bring back ice, the opposite of what you said. And we got to bring it back because all of the things that are happening with the disappearance of ice are causing immediate, very harmful effects on the planet, like increasing the rate of sea level rise from the loss of Greenland ice, and increasing the threat to the planet, for instance, from a methane outbreak in the Arctic Ocean, which is allowed to happen when the sea ice disappears. So therefore, the Arctic has been identified as by the organization here, but also by other organizations like, for instance, the Cambridge Climate Repair System, where network from David King, where they have identified 3 targets to save the world. One is reduce our carbon emissions. Number 2 is remove CO2 from the atmosphere. But number 3 is bring back sea ice, bring back ice. So I'll leave it there and let Leslie tell us how we can bring back ice.
First, thank you so much, Peter. What a privilege to be following you. I think I'm the one being recording, so I'm trying to get it so it will pin on speaker as it was on you. So now I'm replacing pin. That was fabulous. I think you need to stop sharing your screen so I can start sharing mine.
Okay. Yeah.
But that was amazing. Thank you. I learn so much from you every time I hear you speak.
Okay. Well,
I'm going to try sharing screen and see if it lets me just replace it. Maybe.
My IT expert.
Oh, I that. Okay, good. And let me try to start this from the beginning. And I've got actually a suite of people that I can see, which actually makes me happy because I don't feel like I'm just speaking into space. And welcome everybody who joined us. I've been glancing and so many old friends and new. Really appreciate this. So yes, I'm here to try to inject a little bit of hope into this dire circumstance. And I will say that I have been, as Tom so kindly mentioned, been teaching at Stanford. This fall will be the 12th time teaching my class on engineering, entrepreneurship, and climate change. And my students come in so worried. And a lot of the questions they ask are, we can't possibly, adhere to the 1.5 degree target. Are we doomed? Or the 2 degree? And really, it really is true that every degree does matter, and every degree that we miss by is going to make things unimaginably worse. But the worst thing we can do is just give up. So let's not. I met Peter years ago. I met Peter well before goodness. I'm trying to get a control thing out of my way so that I can see clearly, but it probably isn't bothering you at all. Gosh, and I'm looking at the panelists. Here's this book, Ice in the Ocean. And this is how Peter and I first met, or how I first met him. As Tom mentioned, I've been at this looking at ice for quite a while. In 2006, it became obvious to me from looking at the Gore movie, An Inconvenient Truth, that my kids were going to be impacted by climate change in their lifetimes, and it was likely to be bad. And what could I do? And long journey of figuring out what I wanted to address on this, and ice really looked like a key lever on this. And so I found Peter's book in the Stanford Library. And I pasted that thing with about a couple packages of Post-its. It was so good. And so I was absolutely thrilled. I think it must have been late 2006, Peter, when I wrote to you and said, I've got this project I'm starting. I wonder if we could speak. And I was just so thrilled when you said yes. And so that has started a long and very useful, very helpful and encouraging relationship where I get to learn from one of the world's true experts. So thank you, Peter. I just can't, I'm so honored to be speaking with you. You've seen part of this here, and I think we're going to try not to make this be a very long presentation, but I will start it and rush through it a little bit. Peter has shown you bits of this, right? That the ice used to be a lot in the Arctic, multi-year thick ice, which means over 4 years old, and it has become far less. And so if I forward this a little bit and race through it a bit, you'll see we used to have, as Don Perovich, who was our most recent webinar participant before this, another world-famous ice expert, was showing, he was talking about this as the beating heart of the ice in the Arctic. You can see seasonally, every month, every year, it's changing. It's melting as you get towards summer, it's regrowing in the winter, but the thing is it's coming back with less and less of that bright multi-year ice. And fast forwarding to where things really start grim, you can see we're going to take a sudden downturn. We have an enormous amount of ice export through the Fram Strait. This is the Beaufort Gyre, the historic nursery of multi-year ice. And this is where we've done some field testing, small field testing you saw in Vice Media. Whoop, I didn't mean to stop that. Up in Barrow or Utqiagvik, Alaska, which is its real and resumed name. And you can see the multi-year ice, it's just basically gone. There is very little left. And the problem is, open ocean is very dark. First year ice is also pretty dark. When you're growing fresh ice and it's only growing on open ocean, it's by definition not multi-year ice. It's thinner, it's less reflective, and that means that it melts more quickly. And what you've probably been hearing a lot here in this talk so far is albedo. And what albedo means, the ice albedo feedback effect, the thing that's really been affecting this, the albedo loss is quite substantial. And the albedo loss is meaning basically just loss of brightness. And so two wonderful experts, right? Peter has been saying that the loss of ice in the Arctic, I guess I have to minimize this so I'm sure the recording picks up these slides. The loss of ice in the Arctic of that reflectivity could be adding as much as 50%. That's if you count the loss of albedo in sea ice as well as land ice. And Don Perovich, is quoted in these Arctic report cards that come out in December from NOAA, National Oceanic and Atmospheric Administration. Back in March of 1985, it was about 30% of our Arctic sea ice cover was this nice, bright, reflective heat shield, as we like to call it, and now it's about 1%. So that's a big deal. So when you think about that, you're thinking, well, what could I do about it? And one of the things is I've come to realize this is not simply a technical solution. A colleague, Danielle Chamberlain, has put this together, and it's a beautiful thing. Again, I'll fast forward it a bit, but the idea is you cannot solve a problem like this just thinking about the technology. There are so many things you need to consider, and you need to get them in the right place, right? Academic institutions, scientific organizations, government labs, native peoples, policymakers, early stage research, absolutely, lab testing, deployment research, climate modeling, these things. We're working with experts in all of these. Effectiveness in the field, we like to call that ice truthing rather than ground truthing. And you can see a picture slowly appearing here of some actual field testing we were doing with, many of you are corresponding with our principal engineer, Alex Schultz, who's behind the chat there. This was Michael Thomas, who taught me to drive a snowmobile. He's part of the UIC science crew we work with up in Utqiagvik, and this is me. And this ecotoxicology and fate studies is an absolutely key part too. You have to make sure that you will first do no harm. Don't make things worse. Steve Schneider, when I first was presenting this idea to him and Terry Root, his wife, just phenomenally wonderful climate scientists. The first climate scientist I was telling about this, Steve was just looking me in the eye and saying, there are a lot of ideas of what to do about these things, but just for Pete's sake, make sure you don't make things worse. And so we call our first principle, first do no harm. I think it really is. We're trying to do a Band-Aid for the planet to give time to do all that decarbonization of the atmosphere and the economy that Peter was talking about. Our material of choice at this point is hollow glass microspheres. We've tried many, many materials over time, and you saw it in the Vice Media thing. I guess I'll turn on my picture again so I can be sure I'm showing this to you. It's just, it's a little white powder. I can pull it out of this little jar and flow it onto my hand, and it looks like, it looks like face powder, but it's very white. And these are commercially available. They're very widely used in many, many applications. In fact, I found an HGM now being approved by the FDA or in the process for delivering a cancer therapy using a porous version of this. I chose it because this is something that is rather nature-based. We have a lot of silica in the environment. It's one of the most common things in the world, so silicon dioxide. And so it's in marine and land ecosystems. And I wanted something that was going to be commercially available, widely used in a lot of applications, so that if we decided that eventually we wanted to get this done, it seems like it'll be when our backs are against the wall. And so you want to have something where you don't have to bring up an entire supply chain suddenly, an entire new industry. So it seems a very practical choice, and it's very different than plastic. And so that's a very important thing. It won't attract oil-based pollutants. It doesn't cause an ingestion harm. With every test that we've run so far and all the literature out there, so far all looks safe, but we test. And we're raising funds to collaborate with a team of marine biologists in Norway at Sintef Oceans, which is very exciting to us. So, the only way we're going to get the job done before that ice-free summer that Tom and Peter both talked about, possibly by 2030 in the Arctic, is to collaborate worldwide with the experts who can help us along quickly and who also give us a sort of outside peer review, if you will, while they're saying, well, that approach, we need to massage it this way. I mean, we need that kind of feedback. It's absolutely essential. This is what I call my magic slide, because I think this, more than anything else, explains what the heck are we proposing. So you saw from that ice video, the melt satellite imagery from NASA that I fast forwarded through that movie. And when we have open ocean, we're only reflecting about 5%. of the sunlight. And there are, there are angles, there are waves, but this is the generally accepted measurements. A lot of these measurements come from Don Perovich's work up in the Arctic. He's done a lot of albedo measurements. Young ice, it varies. Does it have melt ponds on it? Does, many, many things, but about 30%, so more reflective. Bright ice that's been ripening maybe has a layer of snow on it, much more. And the story is that when we put on a very thin layer, about a hair's width layer of this materials on selected areas of ice, the thought is, the measurements are saying that we up the albedo, we don't get brightness, we don't get all the way up to this high reflectivity right away. Over time, the climate modeling is suggesting that we have a potential to actually regrow multi-year ice, not just make it last longer into the summer bit by bit by bit, but actually eventually regrow it, which is really exciting. And it's, again, trying for the smallest intervention you could possibly have is the least risk. So bare ice at a test pond we were working at in Minnesota. Alex has spent several weeks there lately with the residents there and really working together to get this done. Bare ice, snow, and then treating it with these HGMs, hollow glass microspheres. You've got a substantial difference in reflectivity as soon as you apply it. Here we are. We always work with the collaboration of local residents. So here we are in Alaska, drilling an ice sample. We've snowmobiled out there. There was we had a wonderful instrumentation volunteer years ago, and there's another part of the UIC crew. I think that's Charles. And, just working away to set up instrumentation to monitor what we're doing. And here we are on this pond in Minnesota where we've just worked again. We've worked many years, just measuring what's happening. And you can see as soon as we put this out, this is regular ice, nothing, we haven't done anything to it. And this is with our material on it. And even, this is some drone footage, which was really nice, even after the melt, where the untreated side melted out and the treated side still persists in brightness and has some ice underneath it. Small pond, you aren't going to have a very long-term effect, but you can still see traces of how it was deployed here, square by square. Just carefully monitoring materials into that still persists after a number of incidents of having had it snowed on and rained on and melted. So that's really pretty exciting. The climate modeling is showing us that we can go ahead and treat selected areas of the Arctic and have an impact. The first area that our climate modelers, experts from Climeformatics with Arctic Ice Project, which is us, we asked them to model the Fram Strait. They wanted to model the Fram Strait because that is an area through which a lot of ice is exported, and it looks very impactful. But it's a lot of work to do something as radical as this and get it really ready for that superb level of publication that we hope will convince policymakers that this is an important thing to do. Certainly the Beaufort Gyre, for all kinds of reasons that Peter has been describing, is incredibly important as well. And the aim is we don't want to carpet the Arctic. We don't need to carpet the Arctic logistically and cost-wise. That would be pretty tough. And so what we did basically, the short story here is that we took one of the biggest problems in climate change of, wow, the Arctic ice melting is causing a host of difficulties, and tried to turn it on our head and say, well, then that's a leverage point, right? Challenges become opportunities. So that's where we are. And I think that's my last slide. I have a couple of slides for human interest if anybody gets interested in those, but that's the end of the official presentation by me now. And thank you so much.
Thank you, Leslie. Thanks, Peter. We've been having a lot of questions come on through Reddit and that are being chatted to us. And so we'll try to get through as many of those as possible. I also have a couple questions. I think some of the questions are very detailed. I'll save some of those for the end. But those were fantastic presentations. And Dr. Wadhams, I kind of like the fact that there's so much to talk about, but you brought in the voice of the poor in terms of how climate change is going to affect agriculture in the least developed countries. And I think that that's something that is missing from a lot of these presentations. And Leslie, it was a great segue in terms of one of the potential solutions and how we can save the Arctic. One of the first questions I have, which is you already touched upon, but I think it's good to go into a little bit deeper, Dr. Wadhams, just for our audience, is in terms of adopting a more comprehensive climate agenda. And so one of the questions that kind of asks that is, this is the question, is reducing greenhouse gas emissions alone sufficient to save the Arctic?
I'd say no. Well, first of all, it's not sufficient to save the world, and I think one of the biggest mistakes that we're making, and is still being made by very serious climate scientists, is that the continued emphasis on reducing our emissions, and the way that's been playing out now with the latest Intergovernmental Panel on Climate Change report, is that we have to keep warming below 1.5 degrees, and we can only achieve that by bringing down emissions to zero by 2050. And of course, that's completely impossible, and it can't be done, and it won't be done. And so there's a fraud going on, in a sense, that the people who say we're going to do that know that we won't be able to. And the only way actually to save our planet and bring keep the temperatures from rising to a point where they cause a kind of catastrophe is to take the carbon dioxide out of the atmosphere, because it's carbon dioxide, as we learned in 1896, it's carbon dioxide which is causing global warming. So if we can take it out of the atmosphere, we can cure global warming. And it's therefore, all the research that's being done now on air capture or ocean capture of CO2 is absolutely vital. That's what we should be putting all of our effort into. It should be like a Marshall Plan or something. But instead, we're still talking about just reducing our emissions, which is not. It means we roast to death more slowly if we just reduce our emissions. We have to take it out of the atmosphere as well. So this is independent of the Arctic. I mean, the Arctic, we want to try to cool that and bring back ice independently of what happens to the world as a whole, because of the particular threat for the Arctic. But for the world as a whole, we have to take CO2 out of the atmosphere and not just try and survive by reducing emissions.
And I would like to
Yes,
respond.
please, yes.
Yeah. The Arctic, the point of what we're doing is that it is going to take a lot of time. I was learning this at Stanford when I was getting interested in, climate change. I'd better take that on. Those were not the fields I majored in. But it became pretty clear from some of the wonderful meetings that Stanford had and some of the experts I was talking to how long it takes to turn over the infrastructure, even once you're serious about it. And, it's hard to demonstrate that we're serious about that yet. So that problem is going to be with us for quite some time still. And even if we were to stop right now, the old chemical engineer in me, the first set of degrees, says that we haven't equilibrated to the set point we have right now on the CO2, on the composition of the atmosphere. We have changed the composition of our atmosphere. And so we're still equilibrating. We stop all emissions today. We don't do anything else. We're still got temperature rising there. And as I was looking at all of that and then looking at the Arctic, it was, we need some Band-Aid. We need some intervention that's going to slow these accelerants that Peter's been describing so eloquently of, anything that you've got already going on with CO2 gets worse if you reduce your reflectivity in the Arctic, because you're warming the oceans and air, and they are feeding back to the rest of the planet as well. So one simple summary that I have is, yes, you've got to do exactly, Peter. You've got to pull the CO2 out. We've got to stop emitting, for Pete's sake. And we also have to get the Arctic reflectivity back. And the whole intent is to give us some more time with less devastation to get those incredibly important other jobs done. The job one, as you say, the CO2, address the greenhouse gases, and hopefully prevent this, possible spike in methane emissions, which would be dire indeed if we let enough of the Arctic melt. So it's kind of many problems together, really bad issue. I didn't mention in my talk, but I'm going to wander off on this for a second. We are beginning to assemble a collaboration around the Himalayas and Greenland. We've been approached to do that, and to work on the Himalayas, and then with that, we're saying, if our techniques help with that, then they could help with Greenland as well, because these are dire problems too. Sea level rise, loss of stable drinking water for billions of people. And that's going to be some exciting discussions. So if you're interested in helping promote that in some way, we'd be interested in talking. That's going to be a very important thing. Of course, we're not the only technology in town, but we seem to be the one that's reached technology readiness level 3. We've gone through proofs of concept and all these things. So thank you for letting me put in the other points.
No, it's great. And I think it hits, especially for the layperson audience, kind of one of the dirty secrets about climate change, which is reaching net zero emissions isn't sufficient. There's actually more work to be done. And the scientists know that, but not everyone else does. One of the other questions that's coming through that are a paraphrase for Dr. Wadhams and you, Leslie, is it's a question that I often get too, which is, to be direct, is it too late to save the Arctic? As a polar expert, we're speaking about, potentially an ice-free Arctic as early as 2030 or the next decade or so. Why are we starting our work in the Arctic rather than a different polar region?
Well,
you go first, I'll go second.
It might be too late, but the trouble is, if it's too late to save the Arctic, it's too late to save anything. We may be in a position that we've reached through inaction since 1896, that it's now, and especially inaction in the last 20 or 30 years, it may be too late to actually save the planet. We're not, as the Mauna Loa graph shows, we're not doing actually anything about reducing carbon dioxide levels in the atmosphere. For everything that the politicians have been talking about for the last 30 years has been basically, a falsehood. That is to say, they've said we must take emergency action about this, and then there's been no action at all, because as fast as we've tried to reduce our emissions in some direction, we've increased them in another. So we switched to electric cars, and then everybody buys an SUV. So there's the human race is possibly terminally stupid, and we may be too late to save the Arctic and to save the rest of the world. But you have to hope that we're not. Otherwise you despair, and you have to hope that the case for taking carbon dioxide out of the atmosphere, for instance, can be made and accepted, and a big enough effort can be put into air capture or whatever other capture we do to take it out of the atmosphere. And that includes sea ice regeneration. If we can find techniques that work and that can bring back sea ice, we should do that as a high priority. So we have to hope that we can solve these problems, and we're, well, as Leslie's an engineer, a chemical engineer. I'm a physicist, but I've become an engineer since I moved to Turin Polytechnic, which is full of engineers. And engineers try and do things and make them work, whereas scientists try and find out things. But what the world needs now are engineers to do the things that are needed to save the world.
I love that. Actually, my class, right, it is filled with students who are trying to figure out what could they do to help. I think, Tom, in answer to your question, I really think this quote that I keep hearing is true, that it's within the next decade that we have to take substantial action. It's the last decade in which we can. and have enough of a difference to change the future, to give our kids a future, basically, which is my skin in the game. And it's it really matters, and it takes all kinds of people. It takes scientists to tell us what the reality is, Peter. I mean, that without your book, without expertise like yours, we don't know what needs solving. And it takes it takes all kinds of people to help. For me, I like the idea with engineering, you can put your inventive hat on. It's like, gosh, is there a way to restore that lost functionality of reflectivity in the Arctic, and brainstorm about it? In a weird way, that's an awfully fun thing to be doing, is working on a problem that really needs to be solved, that has so many dimensions. In another way, it's hard to keep your stress level down when you read every single article that comes your way on this. It's like, ah. So it's it takes a lot of different people. Our climate modelers, modeling how do we take? So I see Alex on my screen, our principal engineer. He instruments these tests so we can figure out what's happening, and then we take that data into the climate modeling, and then the climate modelers show what on earth happens in a teeny part of your testing. What influence could that possibly have on the world? And that's incredibly important. And so it's a whole partnership. We're so excited about these marine biologists in Norway that we'd like to get to work with, and national labs. And there's a lot of collaborations that can help us take our rather small base to try to get the job done in time. And I think that's the only way it's going to work, is to have a large enough, collaborative, expert enough team to get the job done.
Well, that's actually a good segue to ask a question to you, Leslie, as an engineer as well, which is we're doing a lot of navel gazing. And Peter mentioned that, we should act as if our lives depend upon it, even though it's our children's lives that probably depend upon finding a solution. And one of the questions that came through for you, Leslie, is how does this work get funded? We're currently in a situation where the government funding hasn't arrived yet. So how currently do we fund? The specific questions is, how do we fund our current projects for large-scale deployment?
Well, we're not ready for large-scale deployment yet. It's one, because there's a number of questions. We're giving ourselves 5 years to finish answering to the satisfaction of the world, we hope, right? Yes, we need the calm science I'm seeing coming across, exactly. But we're trying to get all the answers on safety and efficacy and cost, and any unintended consequences. Do we need to change our material set slightly? All of that careful work. Looks like it would take about 5 years to finish, with a lot of really great collaborations assumed, if we have enough funding. But I started this as a volunteer. Many of the people who are helping us a lot to this day are volunteers. And we have a small, lean core team as well, but it's it's something that there isn't enough funding for, and we make decisions that are really decisions because, well, we're testing there because it's what we can afford to do, and so it's very constrained. How we've had our funding so far has been thanks to some incredibly generous people who heard what we were up to and wanted to channel, I love this phrase too, they wanted to channel their climate anxiety into action. They wanted to help us by getting the word out, by giving us, donations to let us keep going. And so we are a nonprofit, and we are, fighting hard to get enough funding to get the work done. And it's frankly hard work. And Carol, would it make sense to ask you to say a word or two? Carol is one of our board members who's a champion fundraiser, as well as Tom is out there fundraising. I'm out there. It's a team thing. Robert, is doing a lot of the outreach to make these things happen. But Carol, do you have a word or two about that?
I think it's important to say thank you, Leslie, that where you say every degree matters, every degree is worth fighting for. We kind of feel like every dollar matters and every dollar is worth fighting for, because even the smallest donation makes a really big difference. So
wonderful.
Thank you, Leslie. And Carol. And I had a specific question that came through for Dr. Wadhams. I think it's, you kind of alerted people to the ticking time bomb that's underneath the Arctic in terms of the methane. And the question was, how much of the methane threat is underneath the Arctic ice versus the methane threat from the Siberian land-based permafrost?
Well, well, it's actually the immediate threat is underneath the Arctic ice, because the thawing of the permafrost layer on the seabed is going on at rapid rate. In fact, the very most recent field operation by this Russian group of Natalia Chakova has been filming the rising of methane plumes from the seabed. But more frightening about that is that it's not just methane plumes that have been rising, but it's something that looks like kind of sheets of aluminium coming away from the seabed and rising up through the water. It's actually sheets of the permafrost disappearing up and up. So it's not the methane plumes are not just breaking through the sediment on the seabed, they're breaking through and breaking up this permafrost protective layer. So the permafrost layer is a bit like a pressure cooker. The pressure cooker is holding down the methane, stopping it from turning into gas and coming out. The pressure cooker lid goes away, the methane will turn into gas and come out. And it could all happen very rapidly. We could get 1 or 2 degrees of warming worldwide all of a sudden. And goodness knows what that will do to the planet. So that's the fear that many people have, and I have especially, is that the methane from the Arctic seabed could all come out in one very large burst. But in the long term, we inevitably will get a lot of methane, in fact, larger amounts coming out from the thawing of permafrost across the whole Eurasian continent, and that's where the permafrost in cold terrestrial areas is thawing, and you don't immediately get methane. You get methane being generated by various processes that then happen when you have these nasty organic material that was frozen. It's a bit like when you've had something in your freezer too long. It's harmless as long as it's in your freezer. Then when you throw it into the garbage, suddenly something horrible happens, and that's what's happening. It's coming out and turning back into soggy, nasty, rotting organic material, which is producing methane. The total methane that's waiting to be produced by the continent of Eurasia is greater than the amount sitting under the Arctic Ocean, but it will take a few decades to all come out. We'll have a slow methane effect or a fast methane effect. It's not clear which it's going to be, but it's going to be one or both.
Thank you. Terrifying, but thankful. The next question, I guess, to both of you, but I'll start with you, Dr. Wadhams, is when we talk about some of these climate repair approaches, of which Arctic Ice Project has one, for example, what do you think is more complicated? What is the greater risk in terms, is the technology more complicated in terms of vetting it for safety and effectiveness, or the governance?
Well, it's this difficult one.
It's hard.
I think it's the technical problem, but most people seem to think it's the governance, and the reason is somebody that I respect very much is Stephen Salter, who's an engineer in Scotland who developed the marine cloud brightening method of trying to put a sticking plaster on global warming by releasing very finely divided seawater into clouds and brightening the clouds. So it's a form of geoengineering. And he said, I wish that when I see scientific papers or papers about marine cloud brightening, there's about 50 papers on the governance of marine cloud brightening for every one that actually tells you something useful about how you do it, because there's nothing like a sociology department in some university to ponder on the question of how do you control or govern how you do a repair job on some aspect of the climate. And it's easy to write, I mean, to be cynical, it's easy to write a paper on that, and you can get lots of publications and promotion and so on. But the actual physical question of how you do it is much more difficult. So anyway, that's I just wanted to say something to Tom about poverty, because he said I'd mentioned the effect on poor people of climate change, and but that was with respect to another aspect of the fact it affects the poor worst. But I think the biggest way it affects the poor worst is actually sea level rise, because sea level rise is accelerating, and that's causing flooding. And the flooding is happening in poor countries like Bangladesh, where you've got huge populations living right down at sea level, and they can't afford to build any flood defences. And so there's going to be massive amounts of losses of life and losses of livelihood from sea level rise, especially. And that's something that people don't, they complain about, well, Miami is going to disappear and Houston's going to disappear, but not sort of several million people are going to disappear from Bangladesh, which is the more immediate reality.
And likely accelerating the risks of wars, right? I mean, if you have no livelihood and no home, I mean, there have certainly been wars fought over less. I wanted to answer this too, Tom. You know, we concern ourselves a lot with this governance and policy because we think, you know, as an enthusiastic inventor, I don't think I'm the person who should decide whether this approach is in the best interest of humanity. That doesn't make a lot of sense. And so we try to provoke the governance and policy discussions that we hope will lead to, you know, how do these frameworks get developed? And we found some nice allies at NCAR in Colorado, Boulder, Colorado, who have this CCIS program looking at this whole, what is the structure of how you make these decisions? And the AGU, American Geophysical Union meetings, and EGU, so European, same thing, are looking at these questions. And we are intentionally provoking a lot of conversations about this. At least we're getting to hear from the experts on what, but as a person trying to, as an organization trying to develop a solution, we need to know what the frameworks are. So that if it costs this much, if it has this unintended consequence at this level, but this benefit at this level, what are the guardrails? And so those are just things that I think anybody developing a solution like this needs to have in mind. And we're really trying to figure out what are the rules or what should they be. And Tom, if I can segue into a safety question I saw in the chat a bunch as I had a chance to peek in. A lot of people are concerned, will these things become airborne, these hollow glass microspheres, or, you know, are they a hazard? What happens if something eats them, right? That's one of the main concerns anybody has with a material solution. All the tests so far say everything looks good, but we haven't run all the tests. So we have had it fed to a fish species, a bird species, no problem. What the manufacturers say about specifically the one that we're using this year in Minnesota, no problem. This thing that, you know, they're doing drug delivery of a cancer therapy within a porous hollow glass microsphere is extremely, FDA looking at that carefully, and I think giving approval. In fact, I know that of at least testing. That's really encouraging. Once these things hit the water, they're hydrophilic. I chose that on purpose. Hydrophilic meaning they like water rather than oil. I wanted that for a couple reasons. One of them is they're more effective that way, as far as we can see. But they also won't attract oil-based pollutants, so if something eats it, it's different than plastics. Plastics will pick up oil-based pollutants. They're like the oil in your oil and vinegar. This is like the vinegar in your oil and vinegar. It doesn't want to pick up oil. And then lastly, once they've hit the water, if they have water on them, they're not going to get wind blown. The one material we've seen that got wind blown off the pond in Minnesota turned out to be a completely different kind of material. It was a ceramic rather than these hollow glass. So we've been looking at it. Everything's good so far, but we really are fanatic about test. You know, we haven't tested everything we need to yet. And if we find a problem, we'll say, oh, well, we need to change it in this way. So safety first. Anyway, Tom, it's hard to tell whether, you know, technology, governance, they play together, right?
There's a diversity of opinions on the topic. It's a common question. So I think it's good that we had that conversation. A lot of questions are coming in. I think we have time for at least a couple more. I do, on a personal basis, as a former country director in Africa, appreciate that what attracts so many people to climate change nowadays is the devastating effect it's going to have on the global poor over the next 10 to 20 years. And we're all working on climate change adaptation. And what we're talking about today is actual solutions to climate change, which is exciting. So two of the questions, I'll ask them both, and maybe Peter, you could start, and Leslie, I'd love to have your opinion too. I'll ask them back to back. What are the most striking changes you've seen in polar ice? And I think on a personal basis, Peter, you've been working in this field sector for so long. I think you could probably go back to your first expedition or one of those few expeditions. I'm sure there was some moment in your career that really hit home. And then I have another question, which is, why does the Arctic warm faster than the rest of the planet? So Peter.
Okay, I can answer the first question, but I'm not at all sure about the second question. In fact, I was just been looking at that recently. Okay, well, certainly the big changes since I first started messing about with sea ice back in the early 70s was this loss of multi-year ice. Multi-year ice used to be in my youth. 60 or 70% of the Arctic was covered with multi-year ice. Really, really serious stuff. That's why ships had difficulty getting through the Arctic, why people had difficulty walking to the North Pole. But now it's down to just 1 or 2%, and it means that the habitat of for polar bears, for instance, has disappeared. And it's a massive change, and I showed some slides about that. So it's probably, apart from the disappearance of ice altogether, it's one of the biggest changes in the appearance of the planet that's ever. So we've been doing things to the planet which we ought to be ashamed of. But that's the ice. The question of why is the Arctic warming faster than anywhere else? I sort of sneakily avoided that. It's warming about 3 or 4 times as fast as the rest of the world, and the conventional reason that's given is that because the sea ice is disappearing and land ice is disappearing, and you're therefore reducing the average albedo of the planet because you're replacing lots of white stuff by lots of dark stuff, and that's absorbing more. That's absorbing more radiation, and especially in the Arctic, where both the snow and the sea ice are disappearing, and therefore the Arctic should be warming faster than anywhere else. And this is a very nice explanation, except I don't think it's true, because you would expect that just to be happening since since the retreat of sea ice started. And the retreat of sea ice didn't start until about 1950. That's when you first get detectable loss of ice. But the multiplier of warming in the Arctic relative to the rest of the world has been happening since the 19th century, insofar as we've got temperature data that go back that far. It's showing this Arctic amplification going right back to the 19th century. So this simplistic explanation in terms of albedo just doesn't work, because the warming has been going on for such a long time. So it's something more complex, which needs a lot more work doing on it, concerned with, for instance, the thickness of the troposphere and other things that are to doing with the Arctic atmosphere, I think. But we haven't solved that problem, and we still have to solve it. And so that is still a challenge as far as I'm concerned.
Wow, I'm still learning from you, Peter. Huh, that's interesting. The answers I would give, Tom, are one thing. So I have not done polar expeditions for decades, but I've been up there, since about 10 years ago. Um, the things that I'm seeing are from satellite imagery mostly, right, to show me these kind of differences. And one thing that Lars Smedzard, another polar expert, has pointed out is that this is such a visible sign of climate change that it makes the case in a way that telling people that a CO2 level has changed is not. So I look out my window here as I'm looking up from my screen for a second to think about the next answer, right? And I can't detect what the CO2 level is with my eye. I just can't. You take a picture of the sky, I can't. But so you have to trust somebody else's instrumentation. And unless you're scientifically minded or tend to believe in the science, that may not be something that convinces you. But you look at satellite imagery of ice loss, and that's something that many people are understanding. And so that's quite important. Peter, I would have gone with the simplistic explanation that as we've lost our white t-shirt in the Arctic, if you will, and replaced it with a dark one, that we are heating up the ocean more, heating up the atmosphere more, and that's just the classic ice albedo feedback effect that I set out to try to interrupt and hopefully reverse. But I'd love to know what more is in the story. There's a lot of evidence that at least that part is true, but that it started earlier is news. That's fascinating, and potentially awfully important.
Thank you. Well, definitely if carbon dioxide emissions were black, Leslie, it might be easier to advocate.
Right.
Right. So that's a difficult point. Listen, we've reached the 90-minute mark, so we're going to move to an after sessions kind of Q&A, where we're going to invite people to virtually ask their questions in order just by virtually raising your hand, and then we'll invite you to ask the questions directly. Before I realize people might be dropping off the 90-minute mark, so I also wanted to take a second to just thank our panelists for joining us, especially you, Peter. I know it's probably closer to 10 p.m. in the UK time, and you need
no, actually I'm in Italy, so it's even later.
Thank you so much. What an honor to be speaking with you.
Yeah. And I want to thank our audience for dialing in today, and while simultaneously thanking the audience for dialing in, I do want to remind everyone, like Leslie and Carol mentioned, that we rely exclusively upon private philanthropic donations to fund our work until such time that our governments get their respective acts together and start funding the science behind climate change. So right now we're actually raising capital to execute on two research initiatives that I think Leslie touched upon. One is climate modeling in conjunction with NASA's Earth Exchange in advance of a peer-reviewed research publication. And another is materials testing on 7 different types of hollow glass microspheres in coordination with Ocean Syntef, which is a Norwegian research laboratory, which would allow us to do materials testing in Arctic simulated conditions at their state-of-the-art facilities. And so just know that your contributions, every degree matters, every dollar matters, would help us execute that research sooner rather than later. So I'll stop there. And Robert, I know you're kind of handling the IT. Is it possible for you to provide, to do Q&A with people that are on the call?
Absolutely, yeah. You just need to raise your hand and I will move you up. Once you answer your question, I will move you back off. We'll just rotate people like that for the next 30-ish minutes.
And may I be casual enough to add that the SINTEF work has a whole crew of expert marine biologists there. This is going to be a key step in our safety testing, which really has us excited because that is one of the #1 questions people have. The performance, the fate, yes, but how safe are these in those environments is something we really need to know. And Robert, the Q&A, I know how to save a chat, how to archive a chat, but the Q&A, are you archiving this somehow?
We'll be archiving it. I've been working on that this whole time, and I will also be on this chat long after you all are off.
Well, if there's some that don't get answered, I mean, I recognize a lot of these people. I could get back to them personally over the next week or two, if needed.
We'll make sure it's recorded.
Yeah, thank you. Lovely.
All right. The first person to raise his hand was Ray Taylor. I'm going to invite him up right now. There should be a little lag time. Give me a second.
Hi. Hello, it's Ray Taylor in Oxford. I work for Allfed on food security. Peter, I wanted to ask about the release of methane. What's the worst case scenario for how soon that could happen? And if a large amount of methane was released in one year, would you expect the 1 centigrade of abrupt warming within a year of that, or would that be another delay beyond there?
Well, the worst, well, there isn't a worst case. The worst case is that there's about 700 gigatons of methane under the Arctic ice in the various shelf seas of the Arctic, Laptev Sea, East Siberian Sea, and so on. But the people who've modelled it, the Russians who were doing the observations, that's Natalia and Igor, have only put in their estimate a 50 gigaton estimate for a sudden outbreak of methane from the seabed, and that was because they were being very conservative. They sort of said, well, there's 700 gigatons there, but the worst that might happen is that maybe 8% of it will come out in one go. And on that 50 gigatons, various people, including ourselves, did modelling of what that would do to the climate of the world, and it would produce about a 1 degree warming suddenly, except that there's been some more recent modelling done by a lady from the US Air Force who says it will actually bring about 1.6 degrees warming. So,
but what's the worst case for how soon it could happen?
Well, it could happen at any time. It's in fact the last field observations that they did, which was last year. They actually got better observations of the seabed than they've ever done before with movies and so on. And this has been showing this not only the methane coming out of the seabed in rising plumes, but also the seabed material, the permafrost, also coming out in kind of sheets. So it's like it's a bit like the tower block where all the cladding burned. It's terrible, and
are you saying it's underway?
Yes, it's underway. Yes, but how underway it is the question. Is that going to produce a gigantic outbreak within a year or two, or will we have a few years grace? And I'm sure that something is happening and will happen quite quickly. And so that's why there's a sort of desperate desire to find ways to clean up methane out of the atmosphere as fast as it's released. And various techniques are being investigated there that as an emergency, that what can we do? How can we get rid of the methane? There's various ideas of using an iron salt aerosol is one type of research where this is supposedly going to react with methane and get rid of it, but it's not clear that it actually does that.
I have another question about black carbon, but I don't know if you want to move on first,
Sorry.
Robert.
Yeah, thank you.
Yeah.
Next up will be Ballerine. Sorry, I'm terrible with names, but I'm gonna move you up. And should happen in a second. All right, here she is. You just have to unmute yourself.
Can you see me?
We can hear you.
Oh, okay. My question is, you know, well, Russia has been pushed into a corner by all these sanctions, and it's forced them to turn directly to an oil and fossil fuel economy. But now they're trying to use this Northeast passage to ship the natural gas to China, and they want to use it all year round. And now I just read the other day that Putin is going to build more icebreakers. And isn't all that, breaking up the ice in the Arctic there in the wintertime extremely destructive? And another thing, I just read another article the other day, the Pavarti Foundation or something like that, that they're trying to preserve the Arctic because now they say that there are 107 cruise vessels scheduled to go there this summer. So how important is Russian cooperation and not breaking up all this Arctic winter ice?
Peter, may I start with an observation and then go to, I think you know more than I do about this, but I've recently heard at one of these meetings about foreign policy and such that there may be plans among, Russia having access now to more potential mining and drilling, that they are considering upping the production of oil and gas by about 10 times what they've done to date. So I don't know if that's true, but that was an interesting thing. But Peter, over to you, please.
Well, I think there's a lot of this is an artificial escalation of the military side of the Arctic, and people are becoming terrified when they needn't be. And I think the villain who originated it is our old friend Mike Pompeo. When he was Secretary of State, he came to a meeting of the Arctic Council, which is the council of harmless bureaucrats in the 8 countries of the Arctic that have territory north of the Arctic Circle, and they have regular meetings to decide on harmless things like how to do search and rescue and who'll do what. But he came along in his clunky manner one year, last year, year before last, as Secretary of State, and said that there was a terrible threat to the Arctic, military threat by China, because Russia was taking goods through the Northern Sea route, taking Chinese goods through the Northern Sea route. So I don't see why that was a terrible military threat, but because the Northern Sea route is meant to be a trade route. But anyway, he thought it was a terrible threat. And to withstand that threat, America was going to increase its military forces in the Arctic. And therefore Russia would inevitably do the same. So it was an escalation of essentially a very peaceful place, which is the Arctic, just by Pompeo being klutzy. And if you really want some amusement, you should read the congressional record of what he said during his visit to the Arctic Council, because he also said that American scientists, American explorers were the first people to the North Pole, and they were 3 explorers who came from Kansas, which happens to be his home state, and they got to the North Pole on snow plows. So you know, you can imagine 3 explorers perched on top of snow plows. I mean, he meant snowmobiles, but he didn't know the word, and so he called them snow plows. Anyway, that's covered in the latest edition of A Farewell to Ice, which is called Latest Terrible and Amusing Things in the last.
Yes, a sense of humor.
Well, thank you so much.
The essence is, there's a lot of it is got up for political purposes and shouldn't be
But
treated.
not the breaking of the ice. in the
Well, not the
Northeast
breaking of the ice.
Passage.
I'm sorry, but we have to keep a time limit on individuals.
You didn't address my question, which
Um,
was breaking up the ice in the wintertime.
Yeah.
using the Northeast Passage.
Okay, I'll just answer quickly that it has been proposed to actually deliberately do that by opening up channels through the ice, and that would cause. This is a way of actually reducing the ice, not of bringing it back, and it may have some effect, but it will have an effect in the wrong direction. We really want to bring the ice back, not help it to disappear.
Thank you, Peter. Next up is Claire.
While Claire's coming up, Peter, I know that these polynyas, these open areas, lose a tremendous amount of heat, so it's not all bad, right, in the winter.
No, you have to, yes, if you're very, very careful, yeah, it might be that you can get a positive gain out of it.
And just before we move to the next question, I just wanted to call out one of our strategic partners, Secure the Future 2100. I actually chatted the link in the chat box, but they have a really interesting white papers on Arctic ice loss and national security that, I'd recommend people that really delve into the issue as well.
Perfect.
Okay, hi. I just wanted to ask a question because I know that Dr. Leslie, you mentioned something about marine biologists being a part of like the Arctic ice projects and stuff, but is that like something that we can actually do as marine biologists, is be able to help with Arctic ice and like pollution and global warming and all that?
Are you a marine biologist?
I'm looking to be, yes.
Welcome. Well, we're very excited about this collaboration with Syntef Oceans, but we would love advice. We would love to know what to be looking for even outside of that. It's something that none of us in the core team are. It's not our expertise, but it's something that we know that we need to be very, very aware of. So I think you've got our contact info. Would love to hear from you what you're thinking.
So it is possible for marine biologists to be able to help with this sort of thing.
Yeah. Now funding is tight. You may become one of our army of volunteers, which we really appreciate our volunteers. But yes, love to have a discussion.
Okay, thank you.
Thanks.
All right, thank you, Claire.
Yeah, could I just add that it's very important, I think, and the one of the things where it's really important is, could we develop kelp growth as a way of dealing with climate warming by fixing carbon dioxide by growing kelp? That's something we don't know is possible, but it looks like it might be, and we need marine biologists to do that, and also efforts to say use fix carbon dioxide with diatoms. There's tons of marine biology that could actually solve this CO2 removal problem more efficiently than doing it by taking it out of the air, taking it out of the ocean instead.
And I guess following on what you're saying, right? Brian von Herzen is one example. We are not simply concentrating on what we do, but we try to stay aware of what the world is doing. And there are so many promising efforts. If you haven't found them, Claire, look at Ocean Visions. Has had a lovely seminar series on a wide variety of marine solutions. There are so many of these sort of activities out there. Yeah.
All right,
Thank you, Peter.
we'll move
You're
on
right.
to our next question from Frederick. Coming on any second now.
Ah, perfect.
Fred, you just have to unmute yourself.
I wanted to ask about the depth of the shallow part of the Arctic Ocean. It's my understanding that below about 300 feet, the methane hydrate and carbon dioxide hydrate and so on are not stable. I mean, below that, yeah, at 300 feet and below, they are stable and they don't outgas spontaneously, especially when the temperature is about -2, which would be the temperature near the bottom, since we don't have floating ice. It's not salty. Salt water would be at a temperature about -2 before it freezes. So the question is the shallow part of the Arctic Ocean shallow enough that the hydrates could outgas and decompose and float to the surface?
Well, I guess the answer is yes, you're right. You're right in your analysis there. And that is the threat. That if you have water depths of more than about 400 meters, then there's no threat from the methane is leaking out all over the world oceans at the moment for various reasons. But if the water depth's more than about 400 meters, it dissolves on the way up. Methane dissolves in water, and so it doesn't get into the atmosphere. It's harmless. A methane plume just vanishes. But if you're dealing with shallow water, the methane gets up to the surface and gets into the atmosphere before it can dissolve. So we're looking at, and the trouble with the Arctic is that about a third of the Arctic Ocean is less than 100 meters deep. And all of that area is very vulnerable. If the protective cap of permafrost comes away, then the methane will turn back into a gas, and it's unstable as a hydrate at that water depth. It just turns back into gas, comes bubbling out. So the danger is that if the shallow water regions warm up, which they're doing, then the methane will turn into gas and will come out. And that's the threat that's been identified.
I think I'd like to add something that I think I learned from you, Peter, of a good way to explain this is, as long as you've got ice in the ocean, and here's the risk that Tom and Peter and I have been discussing, that maybe by 2030 in the summer we won't have ice in the Arctic Ocean. But as long as you have ice in the ocean, you know that your temperature is not going to exceed the melting temperature of ice. In that area at least, it equilibrates. I mean, all the extra energy is going into turning that ice into water rather than heating things. But as soon as it's gone, all that energy is turned, from the sun, from the 24-hour day summer sun, is going into heating rather than that phase change. So that's a big deal, and that accelerates things a lot, these risks.
Thank you for the question, Frederick. Our next question comes from Laura. I think we have time for one more question.
Hi, thank you guys both so much for this presentation. I was wondering, when we talk about restoring or saving the Arctic, what that means to both of the presenters, and whether there's any, I know this part's maybe too hard of a question, but whether there's any quantitative targets that can be added to that when we're thinking about the amount of sea ice loss and sea ice that we're trying to protect going forward.
I think I'll start with that and have the really expert opinion on the broader view go second, Peter. When I started this, what I was really after was just slowing the loss. But what became apparent after a while was that there's a possibility to actually restore it. And I have to credit Peter Fiakowski, who's championing the idea of climate restoration, to say what you're really doing is restoring. Is like, by gum, you're right. That is actually the potential of what we're doing. The metric, gosh, do we want to build it back up to having 30% of the Arctic ice be multi-year? That would bring us back to what we were just a few decades ago. Is that a reasonable goal? Not sure. But we're working on figuring these things out. Peter, what would you say in the broader view?
Well, I suppose in a broader view, I mean, we're aiming, or the world is aiming at climate restoration. And when Peter Fikowski talks about climate restoration, what he means is we try to get carbon dioxide down to 300 parts per million, which is what it was at the end of the Ice Age. And that will cool the planet down. And in principle, we'd go back to where we were before we invented the Industrial Revolution. But in actual reality, we've gone through sort of hysteresis, we've gone through cycles of change, and we're not going to get back to where we were ever. It's sort of you can't relive your childhood, and so we won't be able to go back in every respect to the way we were, even if we can get rid of a lot of carbon dioxide. So going back to the Arctic Ocean as it was, I don't think that's going to be possible. But we hope we can go back to an Arctic Ocean that has got a lot of ice in it. And that will be an accomplishment in itself. And we shouldn't try in detail to go back to having N% of multi-year ice, because we're not going to achieve that.
Nicely said.
Thank you. I believe that is our time limit for these questions. We are reaching the 2-hour mark, and I think it's time for everybody, for Tom to give the closing remarks. Thank you so much.
No, I'll be echo Lalick to what Leslie said earlier in thanking Peter. We didn't even realize you were in Italy, Peter, so it's even later there. So thank you so much. Robert, are we going to be, can you let the audience know, are we going to be making today's call? Are we going to have a recorded view of today's call on the website or anything like that?
Yes, we will. So as soon as this ends, I've got to edit it down a little bit, and then we will be moving it onto YouTube. We can put it onto the website. And if you really want to know exactly when this goes up, you can email me at rmoss@arcticiceproject.org. I'll leave that in the chat, and please let me know at any time. And also, please follow us on social media. We're on LinkedIn, Facebook, Twitter, and Instagram, and soon TikTok if you're into that.
Fantastic. Well, happy Earth Week to everyone. Thank you. You're the center of the good. Thank you for dialing in today. We truly appreciate it. Leslie, I don't know if you have anything else to say, but we can
yeah, I'd love to. Just say this means so much to me to have all of you here with these fantastic questions, to have this wonderful team that you can see on the screen, to have Peter joining all the way from Italy and way past supper time. Just thank you to everybody for their very hard work, for caring, and for asking all the right questions. And yeah, just thank you to everybody. Tom, thank you for the whole framework of this. Carol, I mean, Rob, Alex, it's just, thank you. It takes a team. No individual's ever going to get this done, but I'm just thrilled to see this wonderful team. And if any of you are interested in volunteering or, connecting us and all of that, please do. I saw Canada being mentioned. We're working our way into that. I'm just really excited at how we just might be able to get this to bloom, the whole world village in a way. Those of us who care, maybe we can get the job done in time. And just thank you so much.
Great. Thank you, everyone.
Thank you, everyone. And happy Earth Week to everybody still on.
Indeed. I guess I'll stop the recording. I had a copy of the recording going too. So.
Yeah, that'd be great. I'm going to be stuck